delighted to be here on invitation from Savas and Brunel as a company, a Bristol-based company, looking to establish links with Brunel University, and the background and the academic side of things is one thing, and also the history for Brunel and from Bristol is something we're intensely proud of as well. So the two together are fantastic for us. What I'm looking to do today is approach things from a slightly different perspective, looking at the back end, if you like, the back end of the title of today, but the front end of the process. So we're looking at how you generate heat in the first place, and looking at the different ways of doing that from variable waste streams. The waste to energy sector, the waste to energy market is a week's worth of presentations in its own right. So we looking at the small end, focusing on the small scale waste to energy, where we're looking at destroying waste at source, on site, to generate heat, and then use some of these fantastic technologies to generate some electricity. So different perspective on things. There are larger applications available, but today it's all about small. In the interest of time, I'm not going to dwell on this too much, but suffice to say that waste and the treatment of waste have been around us and with us for a long time. Started with the Greeks. Everything good starts with the Greeks. In Knossos, hopefully nothing to do with the mine at all, but years and years ago, started looking at waste becoming an issue and what we're going to do with it. So as the years have gone on, there have been various different attempts to improve the way we look at it, with the rakers in London in the 1400s, looking at the fact that waste was becoming something of a problem. Shakespeare's father got into a bit of trouble, fell foul of the law, if you excuse the pun. And as time's gone on, the Industrial Revolution's come on, waste has become more of an issue. We've looked to start to recover things from the waste. We've looked to try and do things to prevent waste. The Toshers in the early 1800s in London, a good example of this. The late 1800s, we started to get into, well, how can we recover some energy from waste? And in Nottingham, they started to look at an early form of incineration, which again fell foul to some of the pollution that was associated with it. So we have tried and looked at different methodologies. So I'm not going to dwell, as I say, on that. The purpose of today is to introduce a different concept, if you like, of small-scale waste to energy, but based on a process of pyrolysis. When we're talking about pyrolysis, back to the Greeks again, looking at pyro for fire and the elysis, the separation of. So we are using heat to destroy, or in the absence of oxygen, to destroy the waste sources that we're looking at. The process, or the technology, here we are a technology company, is based on a three-stage process. The first bit is the pyrolysis section. So we feed waste into section 1, and when we're talking small scale, we're talking about 250 kilograms an hour, circa 2,000 tons a year. We can do 2, 4, 6, 8, 10, and then we're up into the upper echelons of size. So section 2 is the pyrolysis element, where once the waste has been introduced, we prevent oxygen getting in between 1 and 2. And at that point, that waste will be exposed to temperatures of anything from 600, 700, 800 degrees centigrade and above. We can play with that temperature depending on the waste that's coming in. If you want to try and recover some of the product for reuse, we can control that. By the time you get to 3, you have a pyrolysis gas and a char, and we will then put that through a very small mini gasifier, and what you're left with is an inert ash. Typically, from the work we've done with the UK military, that's around 7% of the mass coming in. That leaves you with this synthetic gas. It's not quite a syn gas, but it's a sort of a pyrolysis gasification gas combination. We could, and we do in the larger versions, take that reform that and look at putting that into an engine. But that, different subject, different day. At this point, we will oxidize that gas, and that takes the temperature up to the prerequisite, either 850 or 1100 degrees centigrade, and hold it there for 2 seconds, which is part of the European legislation, the Industrial Emissions Directive. Once it's reached those temperatures, it will feed, that hot exhaust gas will feed through the outside of the pyrolysis section and is your heat source to destroy the waste that's coming in. So it's a self-sustaining unit. Once the unit's up to temperature with an external source of LNG or diesel, the waste will kick in, the temperature will, the burner will kick off, and as long as you're feeding waste, you're destroying it into a gas. The hot exhaust will then destroy the waste that's coming in, and on and on and on. So by the time you get to 6, you've destroyed the waste and you have heat as your output. We're talking about 600 degrees centigrade, so it's quite high temperatures. We can control that, we can do other things with it. And typically it's around 750, 800 kilowatts of thermal energy within that. Again, very flexible, because the focus of this is very much geared on waste destruction. Your waste is your issue, your power is secondary. So from our point of view, we're very much in that valley of death to a certain extent. We're looking at working with some of the companies in the room to say, well, we can give you this heat, we can control the heat we give you, and working together, we can help to sort of scale those walls, because what our customers are looking for is not just the heat directly, but it's something a bit more tangible for them. So as I said earlier on, 250 kilograms an hour, designed to run continuously. There will be some maintenance, of course, naturally, but it's designed to be continuously fed. The economics are very favourable, particularly as waste becomes more of a problem. Depends on the application, but because you're not using heat, if you're not using gas, for example, to generate the heat in a hospital or in a factory or facility, you can save anything up to 90, 100,000 pounds per annum, as well as the fact that you don't have to dispose of your waste through traditional sources. So we're encouraging people to see their waste as a fuel source. From an integration perspective, typically, if you imagine the size of a 40-foot container, that's pretty much the footprint that we're looking at. There are, and we have a version which I'll briefly touch on in a second, with the US Army, which is 2 20-foot containers, but the principle's pretty much the same. And this is this bit at the bottom, the electrical generation, where we're really keen to move and expand out into more commercial applications. Environmentally, by treating your waste on source or at source on site, you haven't got the associated vehicle movements taking it to places of treatment. You are dealing with it and recovering it for use locally. The history, I'll touch on the history, dates back to the early 2000s. A company called Compact Power, some of you may or may not have come across, DEFRA funded technology demonstrator in Avonmouth, just outside of Bristol. And that was running for several years on a whole variety of different feedstocks. Typically 8,000 to 10,000 tonnes a year. Latterly, they were looking at clinical waste because that's where the economics really worked out. As a result of that unit, the military, who in the UK can be sort of a forerunner from an environmental point of view sometimes, decided that they wanted to look at something that wasn't incineration, was based on pyrolysis, and so the small-scale unit was born. And there's been a unit on HMS Ocean, the UK's helicopter carrier, for 5, approaching 6 years now. Typically a residue of 7% there. And the military don't use their heat for anything, so we've got a de-superheater on the back, and that just gets chucked out the side. So it's a shame whether it's something they're looking to do something about. There are 4 of these on the UK's new aircraft carriers, 2 on each, and processing, treating all of the shipborne waste. So there will be some pre-treatment from the liquid streams, but sludges, oily rags, clinical waste, packaging, plastics, all these sorts of things are put through a unit because on board a Royal Navy ship, waste is an issue. US Army, the two 20-foot containers bolted together, slightly less throughput. This is about 1,000 tonnes a year because the footprint is that bit smaller. But this is a deployable unit. You can deploy this to remote locations, to difficult areas, and therefore this has a number of different applications beyond a specific site. We've done work with the Gates Foundation and Unilever on sewage sludge. It's an area we're looking to get into from a community point of view. So we're looking at not just sewage sludges, but also how do you combine sewage sludges with solid waste, with plastics, with MSW, with RDF, with cotton, with all sorts of different things that might be local. And how do you combine these liquid and solid waste streams to give a community a consistent output of what we can give is heat, and then what we're hoping to give is electricity on the back of that. So the unit's been in Leeds, it's been down in Bristol on Wessex Water's Janico site, and it's now up in Melton Mowbray, and you're all welcome to come up and have a look at any point. Click through hospitals. The final piece, just to mention, it's not relevant from a waste to energy perspective, but it's a technology that we are putting on board some of the Royal Navy ships, which is a waste destruction technology. The interest comes in the flock that is generated at the end, which is an ideal feedstock for this waste to energy unit. That's a Royal Navy ship, in case you didn't know what one looked like. That then leads us into the final bit of opportunities. With these complementary technologies, for example, that flock maker, you can look at having a hub and spoke method of having small waste producing areas, bringing it to a central core. You can have a central unit, as I say, but anywhere that generates from 500 tonnes a year up to 10,000 tonnes a year. We can treat liquid waste streams, solid waste streams, to generate the heat that can be used directly, or then into steam, or even better still into power on site. So that's where the market's going. We're moving away from purely waste destruction into waste to energy, and as we then go beyond that, we're looking into waste to product. So not only destroying and getting energy and power, but then what can you do with some of the byproducts you're left with? So there's plenty of opportunities on the heat side of things alone before we then start to look at some of the collaborative work we're doing on abatement systems and on all the clever stuff on the back ends.